Okay, there we go. How many elements in period number 2? Tell your partner. There are 8 elements. How many electrons fit in shell number 2? Hi. You need the textbook or this thing?
The quiz.
Oh, the quiz. Oh, sorry, my brain. And I put those right. There we go. There we go. How many electrons fit in shell number 2? Oh my God, you guys are killing me. How many electrons fit in shell number 2 total? 8. So guess what we are doing as we go across row number 2? We are filling up shell number 2. We go from having 1 electron in shell number 2, 2 electrons in shell number 2, 3 electrons, 4 electrons, 5, 6, 7, and neon has 8. So if you are in row number 2, what is the number of occupied shells? That means shells that have electrons in them. If you're in row number 2, there are 2 occupied shells. Can you guess how many occupied shells there are in row number 3? 3. And in row number 4? 4. Row number 5? 5. Okay, that's how it goes. Now, last day we looked at the number of valence electrons. Can you fill in the number of valence electrons for group 1, 2, and 13 through 18? Can you do that down at the bottom? How many valence electrons in group 1? 1. How many in group 2? 2. What's a valence electron? An electron on the outer shell. How many valence electrons in group 13? 3. 14? 4. You can see 1, 2, 3, 4 on carbon, and 1, 2, 3, 4 on the outer shell of silicon. How many valence electrons for nitrogen, which is in group 15? 5. And same for phosphorus. 1, 2, 3, 4, 5. Group 15. And then we would have group 16 has 6. And group 17 has 7. And group 18 has 0. Because remember, valence electrons are involved in bonding. And what do we call group 18? The noble gases do not bond. So if electrons on the outer shell are called valence electrons, can you figure out by looking at this sheet what we call electrons that are not on the valence shell, on the outer shell?
Core electrons?
They are called core electrons. They are electrons that are not on the outer shell. They are on the inner shells. So those are your core electrons. Rows are called periods. Columns are called groups. Excellent. So are you starting to get a feel for all those patterns that we have in the periodic table, especially groups 1 and 2 and groups 13 to 18? What do we call these elements, the ones that are in groups 1 and 2 and groups 13 to 18? We call those the main group elements. And what groups are those? Tell your partner. Groups 1 and 2 and 13 to 18. Okay? So, we've got that. Excellent. Let's move on to this next one. You know what? We've got to go back a little bit and watch a little video. Okay, let me figure out where it is. I think it is here. Nope, not that one. No, 3.1F. Schrödinger and the electron cloud model. The reason we're going to watch this is not because you need to know about this, but what you need to know is that the atom is much more complicated than you are going to learn about in grade 11. Yes? So we're just going to get a flavor of it. This is on page 25. But mostly, we're just going to watch the video. Okay, and which means that I actually forgot to throw this thing on there. Do I have it? No, I don't. Thank you. Okay. Drop off. 3.1 atoms. 3.1 Schrödinger. Click.
Most people have no
Quantum mechanics and the shape of atoms as discovered by Schrödinger.
Okay, so that's what we're looking at. All right, so this is going to give you an idea of what atoms are really like. But don't worry, you're not getting tested on this, but it will give you an idea of where you might go should you go and study chemistry in university. Okay? All right, let's make this bigger. Here we go. I'm going to hit the lights a little bit more so you can see a little bit better.
We all know about quantum mechanics, which is of course the physics theory that describes atoms and elementary particles, how they move around like slushy little waves, and interestingly, it predicts what they look like, what shape they have. It was invented in the first couple of decades of the 20th century by a lot of people all working together. Amongst them were Planck, Heisenberg, Bohr, Davison, du Broglie, Einstein, and of course Schrödinger. These guys already knew a lot about atoms from the scientists who came before them. For instance, they knew that there are about 100 different atoms in nature, and that these atoms join in larger structures such as molecules, metals.
What are these structures over on the left? Those are atoms attached together by bonds. What kind of bonds would these be? Covalent bonds. What do we call these particles? Molecules. Okay, so we got molecules over here. What's this?
Crystal lattice.
That's a crystal lattice. Now, all the atoms are the same. Can you guess what kind of a substance that is?
Pure substance.
It is a pure substance, not just a pure substance. What type of pure substance?
Element.
It is an element, and probably, is it probably a metal or probably a non-metal? Probably a metal, because most metals are solid, and they do tend to arrange themselves in metallic crystal lattices. Now, what do you think he's drawing over here? On the right. Well, let's let him finish it up.
Lattices and salt lattices to make.
What do you think he's drawn over on the right? That is again a crystal lattice. Is that a pure substance or a mixture? Pure substance. What kind of a pure substance is it? Is it an element? No. Is it a compound? Yes. So this would be maybe like sodium chloride, or it could be like calcium oxide, anything where you have a 1-to-1 ratio between the two ions. So this is an ionic crystal lattice. Pure substance.
Make everything we see around us. But what they didn't know, what exactly was going on the inside of the atom. What it was made of, what shape it has. So they were doing experiments on that. And pretty soon they found out that atoms themselves are composed of smaller particles. They found the proton and the electron and they were featherizing the neutron. And with the protons and neutrons, they almost immediately knew what the deal was. They realized that they were clumped in a very tiny core at the center of the atom.
What do we call that tiny core at the center of the atom? The nucleus.
That core was really small. A typical atom is about 300 picometers across, whereas
we have not studied picometers. Picometers are smaller than nanometers. How much is a nanometer? 10 to the negative 9. Picometers are 10 to the negative 12. So they're 1,000 times smaller than a nanometer. So if you start with meters, 1,000 times smaller than that is the millimeter. And then 1,000 times smaller than that is the micrometer. 1,000 times smaller than that is the nanometer, and 1,000 times smaller than that is the picometer. So this is very, very, very small. And that's our nucleus.
the core is typically 0.01 picometers.
Oh.
So this leaves this.
So the atom itself, 300 picometers. 0.01 picometers is the nucleus. So that is about, let's see, 30,000 times smaller than the atom itself. Okay, 30,000 times smaller is the nucleus.
Big open space in an atom, and they realized that this open space was going to be the domain of the electron. But what they didn't know was exactly how the electrons are filling this space. If they are spinning around or orbiting or what. So they made an initial sketch. They called it the planetary model of the atom. Basically the core at the center and the electrons spinning around in big orbits. It was their first idea of what an atom looks like. It proved to be incorrect, but it was a fine enough starting point. It made some very nice predictions and it allowed them to start doing experiments.
By the way, those of you who are sitting, not watching, it makes me really wonder why you're taking chemistry. So it seems like a strange choice to me to take a course and then ignore interesting things, even if it's not on the test. Odd choice.
And they did. One man who was looking at these experiments was a Frenchman called Dubreuil, and he was noticing something very interesting. He found that when electrons were forced to interact with matter, either through some physical process or by hitting a detector.
Okay, so they're saying here's an electron, and we're going to shoot a photon at it. We are forcing it to interact with a particle of light, a photon. Okay, or we're going to throw it through a prism maybe, or something like that.
But the electrons presented themselves as particles, as hard little balls of matter.
Okay, so if you shoot an electron and it hits a detector plate, it will behave as though it is like a tiny little billiard ball. Okay? That's how it behaves. Particles. Tiny little balls of matter. That kind of makes sense to our brains, yes? Yeah.
How do they do that? How do you shoot something like that?
If you get you can actually get electrons to come out of an atom by applying energy to that atom. So you've got your Bohr model here, yes? And you've got, say, an electron in the outer shell. Yes? Now, it is attracted to the nucleus because the nucleus is positive and the electron is negative. But you can rip it off if you shoot enough energy at that atom. Okay? And that's called the ionization energy. It'll rip the electron off and turn this atom into an ion. With me so far?
Yeah.
Yeah. So shoot energy at the atom, electron comes off. Okay? And when the electron comes off, bam, it can go hit a detector. Okay? Now, what kind of energy can do that? You can use electrical energy. You can like have a gas in a tube and you can zap it with electricity. Okay? Or you can actually just shine light at an atom. Usually to get the electron to go all the way off, it's usually going to be like in this sort of X-ray domain. Okay? So like red light won't make the electron come all the way off because it's not energetic enough. Right? Are you familiar with the energies of light? Like red is lower energy and blue is higher energy. And then when you go past that, you get into X-rays. So if you start shooting X-rays at atoms, they will hit that electron. The electron will go, oh, I'm so excited. And it will jump off of the atom because it's getting so much extra energy that it can actually separate from the atom altogether. Okay?
Kind of what you expect them to do. But when the electrons were allowed to move on their own, either by being shot through a crystal or allowed to wander through a vacuum, they always propagated as if they were waves.
So, if you don't have it hit a detector, if you don't have it hit something, if it just moves through something like a crystal or a vacuum, it doesn't behave like a little ball of matter. It behaves like a wave. Ooh, that's odd.
It was almost as if when you stop messing around with the electron, it would suddenly fall apart into some sort of wave function, some sort of probability wave that sloshed around all of space and predicted where the electron was likely next to be found.
So what they're saying is that they're saying like an electron, don't forget to take the flash. Were you here for the flash?
Oh.
Okay, so you take the flash, but don't let the flash get near the flush.
Okay.
Okay? Okay. All right. So if you have an electron, it's really not, if you're not doing anything to it, it's really not a particle. Okay? Even though it behaves like a particle under other circumstances, it's really just a wave, which means this is probably where the electron is. What the heck does that mean? Maybe he'll explain it a little better in a moment. Okay, so we're going to watch the rest of this.
This was the first time they encountered particle-wave duality in matter, and it spelled disaster for their planetary model. Because this model really assumed that the electron stays a particle during the entire orbit and doesn't fall apart into a wave halfway through. So, they needed a new model, but they realized that this model couldn't come from classical mechanics because classical mechanics makes the same assumption that particles stay particles. In fact, they would need entire new mechanics, some new theory that included the wave-like nature of particles. And this is when Schrödinger entered the picture. He had looked at the experiments as well, and he found one common theme running through all of them. In his insight, he saw one law of nature, one equation that seemed to hold no matter what you did. He called it the wave equation. Nowadays...
Okay, first year chemistry, that sucker appeared in my textbook, and I was like, what? Because I had just finished taking Chemistry 11 and Chemistry 12, and even though Chemistry 12 is harder than Chemistry 11, it does not look like that thing. Okay, so that scared me. It was very scary. Okay.
We simply know it as the Schrödinger equation because it was the rock-solid core onto which all of quantum mechanics was built. Schrödinger realized that with this equation he was now in a very interesting position. What he could do is take an atom, any atom, take its properties, stuff like its mass and its charge, all those numbers, put that in that equation, do the math on it, and what he would end up with would be a series of pictures that showed what that atom looks like. He went on.
Okay, he's still doing the math. Yes?
And did it for hydrogen, which is the easiest atom, it's just one proton, one electron.
And did you catch that? This is for the easiest atom, one proton, one electron, and he's still doing the math.
And that one proved to be crucial into unlocking the shapes of all the other atoms. And when he had worked his way through the math, these are the pictures he found. Ladies and gentlemen, the shapes of hydrogen.
Okay, so he did all that math, and that math, you know how math will give you like a curve or a parabola or a thing or whatever? it gave these three-dimensional shapes, okay? I don't pretend to even have the slightest understanding of what's really going on here, okay? Because these are what are called wave functions, all right? So he's going to talk about that a little bit more, and then we'll talk about it a little bit more.
This then is how an electron fills the empty space in an atom, not by spinning around, but instead with its blobby shaped wave function, which we call the orbital.
Okay, so instead of actual shells, like Bohr said, we have orbitals. That's one orbital. It can house 2 electrons. That's an orbital. It can house 2 electrons. That's an orbital. That whole thing, all 3 blobs, it can house maximum 2 electrons. So an orbital can either hold 0, 1, or 2 electrons. Okay?
What I've drawn here each time is just the same hydrogen atom with a proton at the center, and the electron has been allowed to go into a different orbital each time by giving it energy, for instance. And if you look at this one, these 3 blobs together form that one orbital. They house that one single electron. And this one makes a fine example. We can look.
Now, the reason he says they house that one electron is because we are only dealing with hydrogen here. And how many electrons does hydrogen have? Just the one. Okay, so we don't have to worry about it having 2 electrons in it. Okay?
Look a bit at its properties. What you can do in an experiment is take a hydrogen atom and prepare it in this orbital by giving it some energy, for instance. And if you leave it undisturbed, then the electron takes this shape. It becomes this wave function, this blobby shape. And if you then were to take a measurement of the electron, find out where it actually is, what would happen is this wave function suddenly collapses. It condenses into a single point, which we call the electron.
Okay, you remember, if you interact with an electron, how does it behave? It behaves like a particle, like a little ball of matter. So if you interact with the electron, it behaves like a particle. And guess what? So if you take a measurement, that's interacting with that electron. And look, instead of being this blobby shape, this shape here is the electron. Okay? But if you look at it, the electron all of a sudden is a little particle, and there it is right there. Okay? Stop looking at it, and the electron becomes the blobby shape. Start looking at it, and it becomes a particle.
If you then were to re-prepare your hydrogen atom in the same orbital, maybe give it some new energy, then you can do a new measurement, and you can find that electron in the same blob, or in any of the other blobs.
Okay, so the next time you measure it, the next time you interact with it, it goes from being the blobby shape to maybe being here instead. Okay, it becomes the blobby shape again. You measure it again. Oh, now it's here. Becomes the blobby shape. Oh, now we measure it again. Now it's here. And you can do this over and over and over again.
And if you were to repeat this thousands of times, you would end up with a picture very much like this. Notice that there's a higher probability of encountering the electron at the center of a blob. There the probability wave function becomes more dense. So
this is why we call it a probability function, okay? Because probably the electron is going to fall somewhere inside this shape when you look at it. Where are you most likely to encounter the electron? In the middle of each of the blobby shapes. So in the middle of the donut, in the middle of the balloon, in the middle of the balloon, okay? And it becomes less probable to find it the further out you get from the center of that shape.
There's something interesting about these pictures, of course, something that is, well, staring us in the face. The fact that these blobs are not connected. There's an area in between where you cannot encounter the electron. So it kind of begs the question, how on earth is the electron traveling from one blob to another? Is it teleporting or what? This was one of the important questions that led to 40 years of heated debate that ended up with Einstein saying very angry things about dyes. But who cares?
Okay, so in reality, I say in reality, I really don't understand it. It becomes that blob so it can condense into any one of the areas of that blob. That's my understanding of it. And pretty much I have a first year chemistry understanding of this sort of thing. Like I'm not, I did not do my master's in chemistry or anything like that. So my upper level knowledge of it is not so great, but that's okay because who cares?
Schrödinger had made an important discovery. He had found the shapes of hydrogen. And using that as a basis, those that came after him were able to find the shapes of all the other atoms. They are very much based on hydrogen. They use the same orbitals. It's just that the higher atoms consist of more electrons, therefore they require more orbitals to house all of them. So you end up with a situation where the orbitals all get stacked on top of one another, overlapping but not mixing. They do, however, repel, because that's what electrons do, they repel one another.
So when they say electrons repel, why do electrons repel one another? Why does one electron repel a different electron? Because they are both the same charge, and like charges repel. Negative repels negative. Okay?
So the orbitals begin distorting each other according to some very complicated math. But these guys were also good at what they were doing. And combined with Schrödinger's discovery, they had now made a link between physics and chemistry. A link which in fact led to an entire revolution in both of them. So with that, I would like to conclude by just saying, Mr. Schrödinger, thank you very much.
Okay, so just so you're aware, all of this quantum mechanics allowed for the development of lasers and MRI scanners and electron microscopes, string theory, transistors, computers, interstellar molecular spectroscopy, rocket fuel, molecular design, and all kinds of other things. So without quantum mechanics, your phone would not be possible. And I know how excited about your phones you are. What is the other thing you should know about your phones? The microchips in your phones work because they contain
Semiconductors.
semiconductors. And what types of elements are semiconductors? Metalloids. Because that's going to be on your quiz, which is when? Tomorrow. Excellent. Okay. So that's where, honestly, you're welcome to do a little reading about this and whatever. It's just kind of here to remind you. But if you want to read about standing waves, you can read about standing waves. But we're not going to worry about that too much. Like I said, there's some exercises here. If you want to, you can take a look at those. But I'm not going to get too excited about that. All right. What I am going to get excited about is that this is going to actually let us take a slightly different look at the periodic table. Not this one. Where is it? Page 75. Page 75. Now, you know how your periodic table fits nicely on one 8.5 by 11 sheet of paper? Like one of these? Periodic table fits nicely? That's because what they actually did, the periodic table should really look like this. The part of the periodic table we're used to seeing is groups 1 and 2, and groups 13 to 18, which are called the what? Groups 1 and 2 and 13 and 8 to 18 are called the what elements? The main group elements. That's part of the main periodic table we're used to seeing. What's the other part of the periodic table we are used to seeing? The transition metals. So we have our main group elements, we have our transition metals, but in the middle of the table, usually, where do we find these guys here? Usually we find them at the bottom. And what are they known as?
Lanthanides and actinides.
The lanthanides and actinides. And if you forget what those names are, where can you look? You can look at the first element because you'll see La and it'll say lanthanum. And this one will say actinium. And you can look and say, okay, those are my lanthanides and actinides. If we truly drew the periodic table like it should be, it would be this big, and you would need a bigger piece of paper because the writing would have to be so small, which is why we usually chop out the lanthanides and actinides and put them at the bottom of the table. Also, we don't use them very often. How often do you hear of compounds involving neptunium or americium? Not often, yes? So we just kind of stick them down at the bottom and don't worry about them. But the reason that we have these different blocks is that, do you remember those orbitals, those blobby shapes? If you're over in groups 1 and 2, you are filling up the sphere-shaped orbital. Okay? The sphere-shaped orbital is known as an s orbital. How many electrons can an orbital hold? Do you remember what I said? An orbital can hold 2 electrons. So, this is the 1s orbital because it's in energy level 1, it's in shell number 1, and it's a spherical orbital. Sphere, S for sphere. Okay, and we put 1 electron in it, and then we put a second electron in it, and then we have finished filling up the 1s orbital. Okay? Then we go to energy level 2, right? Because we're now on shell number 2. Shells and energy levels are the same thing. We go to energy level 2, and these 2 guys here, we are filling up the 2s orbital. So we put 1 electron in the 2s orbital, and then we put a second electron in the 2s orbital. Okay? Now in row number 2, we get a whole bunch of other orbitals. And they don't look like spheres, they look like peanuts. So can you guess what kind of an orbital this is called? This is called a p orbital. And it looks like a peanut. There are 3 different p orbitals. Three different p orbitals in any one shell, in any one energy level. So you actually have one that goes this direction, up and down. You have one that goes left to right, so they're at 90 degrees to one another. Can you guess which direction the third one goes? If you've got one going like this and one going like that, which way does the third one go? In and out. Yes, it becomes hard to draw it. So the third one goes in and out of the page, which is really hard to draw. Yes, because we're drawing in 2 dimensions. So, if you have 3 different p orbitals, how many can each orbital hold? How many electrons? Each orbital can hold 2. Each orbital can hold 2 electrons. Sphere, peanut shape, doesn't matter. Orbitals can only ever hold max 2 electrons. So guess what? We've got a p orbital. We call the one that goes side to side, we call that px. We call the one that goes up and down py. And we call the one that goes in and out of the board, we call it pz. Yeah? And I'm just drawing little boxes to represent them, but they essentially correspond to these three here. Yes? Let's see, we have px, we have py, goes up and down, and then we have pz. So basically they're three orbitals that look identical, but they just are oriented differently in space. And they can each hold 2 electrons. 1, 2 electrons, 1, 2 electrons, 1, 2 electrons. How many can they hold all together, all three of them all together? 6. Guess what? 1, 2, 3, 4, 5, 6. Okay? 1, 2, 3, 4, 5, 6. So as you go across this block here, you are filling up the p orbitals. So this is called the p block. Oh, I've got that labeled already. That's the p block. Do you remember over on the left-hand side of the periodic table where we had 2 things? That is when we're filling up that one spherical orbital at any given energy level. And so it can only hold 2 electrons. So you're filling up the s block. Now, we're not going to spend any amount of time on this. There are 5. Can you guess what D? Daisy stands for the d orbitals. That's not why they're called d orbitals, but that helps me remember. Okay, D stands for daisy. And this block here, the transition metals, are the d block. I'd like you to count those and figure out how many d orbitals are there. See if you can tell your partner how many d orbitals are there. Does anyone think they figured it out? One person. Anyone else think they figured it out? So there's 10 things there. Are there 10 d orbitals?
Yeah.
How many p orbitals were there? There were 3. And how many elements are in the p block? 1, 2, 3, 4, 5, 6. That's because each orbital can hold how many electrons? 2. So 3 orbitals will let you hold 6 electrons. How many orbitals will let us hold 10 electrons?
5.
5 orbitals. And now you're going to figure out how many f orbitals there are, because F stands for fancy. Because One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. How many f orbitals are there? 7 f orbitals. Now, if you're at all interested, over the weekend, I can give you a little enriched thing. That's a little activity about figuring out how many, about electron configurations, which is something that we should be doing in Chemistry 11, but we usually run out of time, and so we don't get a chance to do. But if you're going to go to university and take chemistry, it will be a useful thing for you to have done. This will help you with that. If you're like, I don't want to take chemistry at university, you can just ignore everything pretty much that I've said today, other than the stuff that was reviewing for your quiz. Okay? So today was a flavor day. Today was a flavor of what you might study later on. It's just to give you an idea. Okay? And if you're like, oh, terrifying, it's not terrifying, it's just new. Right? So, your homework is to study for your quiz tomorrow. I'm not going to give you any other homework. I will put a full detailed explanation of what's on the quiz on Teams. Right now it's sort of a little sketchy, but I know I have it posted somewhere else, and so I'll get you the full thing. So how many people might be interested in the enriched stuff on electron configurations that relate to this? 1, 2, 3, 4, 5. Anyone else? I'll make 10, because, you know, sometimes people change their mind. Thank you. That's great.
Can I take the replace game?
Yep.
Then can I take
Which one do you want to do?
I did request for this and I
Yeah.
got 14 out of 14, but on the
But on the thing, it doesn't say that.
Yeah,
Let's
it
make
says-
sure I change that. So, Caleb, exact, inexact, 14 out of 14. Check again tomorrow and make sure I've changed it,
Oh,
okay?
yeah, thank you.
Yeah.
Very fun. Fun. I think. Well, it's spicy.
Yeah, I was in a restaurant. I have
Yeah. And it's spicy.
I ate.
Oh, not getting spicy.
I really. Oh, I. You have to bear. Actually, some this is during lunch. Are you sure?
That's fine. Yeah, you can do it. Yeah.
Oh,